I would like to talk about distributed sensor networks. I would like to shed some light on ongoing projects and research perspectives, and in that, at least in some points, I expect to be in line with the British view of this area. Let me start with some ongoing results of defense R&D in Germany. Defense R&D in Germany is a low-budget version of R&D, and for this reason we are very much focused on doing good research, good theoretical research as well, but directly focused to the use and the benefit of the soldiers in the field. And distributed sensor networks for the soldiers means that we have to consider multiple distributed platforms, unmanned ground vehicles, robots, drones, unmanned aerial vehicles, and all this in a way that the soldiers can easily command these unmanned platforms, receive information on what's going on, and act effectively then. You see here, it's not a full screen movie, unfortunately, a movie that shows what we want to do. So we have a manned, unmanned platform scenario, multiple soldiers, multiple platforms, robots and unmanned aerial vehicles. The robots and the unmanned aerial vehicles are multiple sensor platforms. They have cameras, they have ESM sensors to identify communication links. They have acoustic sensors for sniper detection, and so on. And the combination of both, several, but we do not talk about swarms, but several, two unmanned aerial vehicles cooperating, interactive, and cooperating with the underlying ground vehicles. That's a tool in the hand of the soldiers which can be very, very effective. Let me stop here and look at the overview. So we have many components here. In the center are the soldiers. The soldiers need information. The sensors need to command their resources in an effective, intuitive way. They need to receive information, situational awareness, and they need to have suggested options for what they might do. When I say the soldiers are commanding the unmanned aerial platforms, I say that they give high-level commands, and there's lots of automation behind it. So it's not autonomous. We Germans do not like the word autonomy in this sense. It's automated. So the human being is always in the loop, or at least on the loop. And part of this automation is interaction of unmanned aerial vehicles and ground vehicles, in that sense, for example, that the unmanned aerial vehicles provide a ground model by laser scanners, which are then used by the ground robots for making their path planning and not getting stacked. So this was an introduction, and it gives you a flavor of what I would like to tell you. And, well, actually, what is the role of sensor data fusion in that? Well, prior to any technical reflection and prior to any scientific work on this area, sensor data fusion has always been the pillar of natural intelligence. All living creatures are performing sensor data fusion. They are fusing heterogeneous sensors. They are combining this sensor information with what they have learned before. They combine it with communications from other living creatures, and from that they create an environmental model, a mental model of the world they are living in. And that's the basis for protection, for orientation, and for achieving a goal. And actually, a clever fox may catch the bird. But even a clever fox can get trapped. Yeah? It's possible that all this effort comes to nothing. And in the same way, in the very same way, sensor data fusion is one of the key pillars of what is now again called artificial intelligence. Again, the wind is blowing from this direction, and of course we are taking up this idea, but there was a wave of this name, actually. So I would say sensor data fusion, the topic that we are discussing here, is one branch, a key branch of weak AI, weak artificial intelligence. By the way, I don't believe in strong AI, absolutely not. But weak AI is a good thing, and we have done weak AI for a very long time. And it's providing what I would like to call, and I would like to call this cognitive assistance, which is a better name than artificial intelligence. We want to support the natural intelligence of the soldier by cognitive tools, and by this, the overall system, cognitive tools, machines, plus the human being is much more intelligent than the soldier without this cognitive assistance. So we wish to understand, we wish to automate, at least partly automate, and to enhance beyond the natural levels what natural creatures, living creatures are doing. We wish to integrate new sources of information and platforms that are available. But by this we are profiting from the main developments, platform technology, sensor technology, communications technology, navigation technology very much. We are able to incorporate database systems which contain a vast amount of context information, also language encoded information, sometimes referred to as soft information. We have unmanned mobile platforms in all the dimensions of the intelligence, surveillance, and reconnaissance circle. And last but not least, but very important, the interaction with human beings. So with this help, with cognitive assistance, we are able to exploit the natural intelligence, the real intelligence, much better than before. So this is the informational basis for manned-unmanned teaming as briefly sketched by the introduction. Well, distributed sensor networks on mobile platforms, that's really the backbone of defense ISR. And we need reliable assistance that, and that's more or less what you said, Paul, exploits large sensor data streams, make context information accessible, optimizes the use of the resources, including a clever control of the platform trajectories, of managing the interaction of platforms, maybe the unmanned aerial platforms providing the ground model, 3D ground model for the robots, optimizing the use of ISR resources. Multifunctional sensors play a role. It checks the plausibility of ISR information, suggests options to act properly, helps respecting constraints of action. That's very important, actually. Constraints of action, that's a humanitarian law. That's the rules of engagements. And we have to design systems, automated cognitive assistance systems, in such a way that we can act properly, even in complex situations. So we need machine assistance to act ethically. Well, that's, I think, an important topic. In the end, our systems need to be accepted by society. And it has to adapt to the intentions of the user. In general, it unburdens the human beings from routine and mass tasks to let them do what only human beings can do, to act responsibly and really cleverly. This is actually the machine that helps us doing this. I said cognitive assistance, cognitive tools. In fact, sensor data fusion is a branch of machine construction. And this is a fusion engine, a machine that is exactly in the middle between the sensor world, the distributed heterogeneous world of mobile sensors, and what the users want to do with this type of information. Fusion engines do not create situational awareness. No, situational awareness only is created in the brain of human beings, of beings that are really intelligent. But the fusion engine provides the information that is necessary for creating, understanding a situation. So it combines all these sensors by standard interfaces, and all these key building blocks are there, including the resources management. So the feedback to the sensors, the feedback to the platforms to make an optimized use of them. There's also external parameters, sensor registration, environment, even soft information, language information. So that means non-sensor information that has to be taken into account. And so the fusion engine transforms data into information, the building blocks of situation pictures. And this is then the basis for decision support systems, for the operators, for doing some things, and for the effectors for reaching certain goals. Well, this the tooth wheels and the power in these fusion engine is provided by algorithms, by mathematics. And these algorithms are developing and evolving at a very rapid pace. The military world was the birthplace of this science, but sensor data fusion is important in autonomous driving. It's important in industrial manufacturing. We call this in Germany Industry 4.0. So also in the civil world, there are strong interest to push the creation of effective fusion engines very much. So we need a modular framework to adapt quickly and rapidly to new developments. And this is exactly, Paul, in line with your stone soup, Thomas, with your stone soup idea. There's one important topic, integrity of sensor and context data. Do the data correspond to the expectations? This is often an implicitly assumed assumption, and it's decisive. It's a prerequisite, but often it's not given. And here the sensor data fusion business and the cyber threat come into a certain link. So this is valid that data are not corresponding to the expectation, can be valid on the level of the signals, on the measurement levels, on the level of classified tracks, on the situation vignettes, and on the mission data. If sensor data or context data are have no longer integrity, then fusion may turn into confusion quite quickly, and management into mismanagement. This can have the reason of unintended malfunction, as we know very well, if the sensor is no longer aligned, so we have to do misalignment algorithms, debiasing algorithms. We know this partly. There can be malign intervention. Sensors can be hacked and become malicious or Byzantine. They are lying. Yeah? There can be unreal artifacts provided by the sensor data fusion, and there are blind spots of the artificial intelligence as well. So things in reality that we do not see but may affect us, and things that are unreal. This means that we have to take into account all these data from different sensors in such a way that we do not accept a certain sensor model and process the data according to the sensor model, but we have to consider both. We have to try to learn and to check the validity of the sensor models while we are processing the data. So both things, learn, check sensor models, and fuse the sensor data. And this can be done and must be done in a rigorous and a well-defined way. And actually, this is a very broad field of ongoing research and a rich field of research which has, of course, direct military relevance. There are 5 pillars, I believe, for distributed sensor data fusion. We have the powerful tools of statistical estimation. We have combinatorial optimization to solve all these data association problems, which are tricky. We have the statistical decision-making, we have the machine learning, we have the control and game theory. These are the power, the engine of doing resources management. These pillars are highly developed and mathematically well-founded. Currently, the ITC and platform technologies are boosting, and driven by economy, we have also this highly interesting deep learning phenomenon. Well, but be careful. So the deep learning that's so effectively on the massive data of Google and Amazon can be applied, has to be used by the military world, but it's not so easy. It cannot easily be transformed because the military restraints are very much different, I believe. I would like now to see into the future. That's a business, a difficult business. How to guess the future of defense R&D. It's a continuous practice. We have a continuous progress in theory. So there is a certain development, but it's always the case. Predictions are difficult, especially when they are dealing with the future. This is a famous saying of a German poet. I have 4 points. I cannot address all these 4 points. I would like to address the first 2 points, but this is my thinking about the future of fusion. We need mathematically exact results. I think it's dangerous to continue to have too much try and error engineering. We need more mathematical results to base our algorithms on a really sound basis. I would like to pinpoint on this. And then we have fusion-dominated sensor networks. So the hardware and even the signal processing is not so dominant anymore. The fusion algorithms themselves say how to distribute sensors, how to process them, how to deal with them. So fusion-dominated sensor networks. There's the big topic of fusion and context information, of language-encoded information, and we have the demand for resources management. I cannot address this, but I would at least like to mention it. Nothing is as practical as a good theory. That's a famous saying by James Clerk Maxwell, the famous British physicist, by Werner Heisenberg, in this nearly the same way by Roy Stride, and many others. In the last century, the 20th century, was the century of physics, one can say. The 21st century is a century of mathematics. So if we have a mathematical understanding of what we want to do, we have the means, the computers, the communications, everything, to transform mathematics into really existing systems. That's a power. So don't forget the underlying mathematics, especially not in a room like this one, which is called the Turing room. So exact formula for distributed fusion, I would like to discuss this with you. So that's one of the bases for doing distributed sensor networks. And I would like to stress on an interesting little animal that we call accumulated state densities. That's the Bayesian approach to multiple sensor tracking. So we wish to calculate iteratively conditional probability density functions that represent all the available knowledge of the targets of interest from different sensors. We have 3 different processing steps: the prediction step, the filtering step, the retrodiction step. That's all well known to you. The likelihood functions contain the full sensor information, the sensor data, plus the underlying sensor models, which have perhaps to be learned before or while we are processing sensor data. And this is the context information on the evolution of the object. Let me make some remarks on distributed fusion. So we are interested in such functions, the probability density function of the state, the joint state of all the targets, given all the measurements in the sensor's field of view. This is the key quantity we want to calculate. And distributed fusion means we want to reconstruct this density from local tracks. That means from such densities that are processing only the local sensor data. That's the key idea. Let us try to reconstruct what we really want from these information. There are many pros and cons. The communications is less overloaded with false tracks. That's very good. Very practical. It's less sensible to registration error or to sensor data disintegrity. And the disturbances of sensor nodes do not lead to total function loss. This is why we are doing this, why this is so very important in designing real operational systems. We have often suboptimal performance. The system reaction time and track quality may be poorer than in another approach, which does not distributed tracking. We have a lacking profit from redundancy and data rate, and it relies on local track existence that maybe can be critical in fusing active and passive data. So distributed fusion is often unavoidable, but it has its defect. There are many algorithms, many approximate algorithms, a whole slew of algorithms which are dealing with this. I don't want to get all through these different possibilities. They are all more or less approximations, better or not so good approximations. In order to get some order, some insight into some structure, into this zoo of distributed tracking fusion algorithms, we have to look at those methods which provide an exact solution which is perhaps in practical applications not to be obtained because it's too too complex and too expensive in a computational point of view, but we need to have the truth as a guideline to bring order into this zoo of distributed fusion algorithms and to help us, the systems engineers, to identify and to choose the right algorithms for our applications. Well, the main problem in distributed fusion is correlation. That different sensors are observing the same stochastic process, the moving target, or the several moving targets, and because of this structure, there are temporal correlations in the data. These correlations are not visible in the measurements, but they are visible in the tracks. So the key to the solution is take into account the temporal correlations. If the local tracks were not correlated, they are. If they were not correlated, track-to-track fusion would be trivial, very simple. It would be just a convex combination of the underlying tracks, of the local tracks. It's now possible with some mathematics, which I cannot show in detail here, of course. Under some assumptions where the Kalman filter assumptions hold, decorrelation of tracks is possible. It's possible to decorrelate these tracks. We assume that initialization is independent, the observations are independent, and if these local tracks are decorrelated, then the locally produced decorrelated tracks are no longer locally optimal, but they are the basis for an optimal global estimate. Let us look into this a little bit deeper. What we want to have in a distributed sensor fusion network, we want to have fusion at arbitrary communication times. We do not want to communicate always, but whenever we are communicating and receiving data from the sensors, we want to be able that the resulting fusion results is then optimal or very close to the optimal. So fusion at arbitrary communication times. That's the key. And this means whenever a fusion result is requested, transform, well, what? Transform a representation of the information of the targets of interest at a given time, which may be a future time, prediction, the present time, filtering, a past time, retrodiction. So if you represent this as a product of Gaussians, then we want to transform the product into a single Gaussian by a convex combination of the expectation and covariance matrices of the characterizing parameters of the local tracks in such a way to get a fusion result. The key question is, can the local tracks, the local estimates, the local covariance matrices, can they be calculated by using only measurements of the sensor S, that means locally at each node of a distributed sensor network? The answer is yes, it's possible, at least under conditions where Kalman filtering is strictly applicable. So when this is possible, then we have a mathematical result to do this. And there are formulae that can be looked up in the papers. In many practical applications, however, the Kalman conditions are not given. The measurements, error covariances are dependent on the sensor target geometry. The sensors have non-detections, gated clutter, or whatever. So we have a strict theoretical basis. When Kalman filtering is strictly applicable, then we can do the decorrelation. What can we do? And starting from this, what can we do to make it more and more realistic and applicable? And here, a new or perhaps not so well-known theoretical construct is helpful, so-called ASDs. ASDs are accumulated state densities. What are these? Accumulated state densities describe the state vectors accumulated over a time window. So we are stacking the state vectors over a time window. We build one big state vector. Well, a state trajectory, if you wish. It's a state trajectory. And want to calculate its properties based on all the sensor measurements that we have collected so far from our distributed sensor networks. So that's an accumulated state density, a state trajectory density, if you want to say it like this. These quantities are interesting from a theoretical point of view and for a practical point of view. Because we are considering a time window, we are able to take into account temporal correlations between the state vectors at different instances of time. And that's valuable. A far more comprehensive treatment of issues in particle filtering becomes possible. That's a family of algorithms that's important. The Q functions in probabilistic multiple hypothesis tracking, a powerful tracking method, are just ASDs. It's possible to formulate exact solutions to the out-of-sequence measurement problem. Yes, that's also a big problem in distributed fusion. If you have distributed sensors, it may happen that the timestamp of the measurements are outdated because of delays and because of latencies. And it's also possible to consider an exact solution to the distributed tracking problem, which is more general than what we have just discussed. So let us consider this. So we are considering ASDs, so probability densities for a state trajectory. If we are considering this as a joint density, and if we are integrating over all state variables, except state variable with time index L, then we are receiving the probability density function of the target states, of the multiple target state, at time L, given all the measurements. So prediction, retrodiction, filtering. In a way, the ASD is the tracking result. The ASD comprises prediction, filtering, retrodiction in one single mathematical quantity. And the Bayes theorem can be applied to calculate these animals, and this looks pretty much what you are very well familiar with it. And luckily, under the applications, no clutter, and not so difficult conditions, these ASDs are Gaussians. And if the situation becomes more complex, more difficult, resolution phenomena, false measurements, multiple targets, whatever, then we have Gaussian mixtures. ASDs characterized by Gaussian mixtures. By the way, these ISDs are very well understood. We have them completely at hand. We have these ASD covariance matrices, where here on the main diagonal you have the covariance matrices of the filtering and the retrodiction, and we have all the temporal correlations exactly calculated. We can invert these covariance matrices explicitly, and that's the structure, a tree-band matrix reflecting the underlying Markov structure of the evolution model. So these ASDs are well understood. Their calculation can be done very efficiently and very quickly because the structure is so well known. So these are not big matrices. They can really be calculated. So Kalman filtering is a building block for the more advanced tracking algorithms leading to Gaussian mixtures. All this is understood. And now let us apply this to the multiple sensor ASD tracking. So for S sensors, S being the number of the sensors, we want to calculate this animal. We apply in a quite standard way the Bayes rule. And the multiple sensor ASD accumulated state density has here the evolution model. And now the evolution model, given by a Gaussian, can be written in such a way as a model up to the power of S, S being the number of the sensors, with a relaxed evolution model. So S is multiplied by the plant noise covariance. So we are introduced relaxed evolution models and then are able to calculate the distributed ASDs in a product way. So for the ASDs, the accumulated state densities, the fused, the central ASD can be written as a product of local ASDs. That's a very fundamental result. So local ASDs contain all the local sensor information. If you're interested in the full sensor information, the fusion information, you just have to do the convex combinations of the ASDs. And this is the exact solution You can do the ASD prediction in quite the same way as you're doing Kalman filtering or extended Kalman filtering or MHD tracking or whatever. This is the filtering, Kalman filter equations or the extensions of it. And in order to realize these, consider a sliding window implementation. So the ASDs contain the full information. Of course, they become bigger and bigger. Consider a small time window, only the last, only the 2, 3, or 4 steps. Then you get a sequence of approximations, and the approximation error goes down exponentially. So only the most recent history is relevant for your local correlations. So let us conclude and have a look at ongoing work. So the distributed Kalman filtering problem, by using relaxed ASDs, provides a mathematically exact solution. No global knowledge on the sensor model is needed. So the way is open to do exact distributed tracking with whatever tracking method you want to have. The problem is increasing state vectors. Of course, we have to deal with this. The fixed length ASDs working on a time window work well. They are not mathematically exact, but they are derived from a mathematically exact methods. A systematic investigation of the errors to be accepted is possible. That's important for system design. The future work is extend this, or the future current ongoing work, I should say, is extend this to more advanced local trackers and do a systematic comparison to the existing approaches. And actually, all these families of known distributed trackers appear somehow as approximations of this exact solution. Well, only a very few slides on fusion-dominated sensor networks. Well, we have a globally available mobile phone infrastructure. This is a map of the world, and this shows that everywhere in the world you have your mobile phone working. Even in these countries, these colors mean that here only GSM is working and not LTE or higher other mobile phone standards is working. So a globally available infrastructure for communications. And the idea is use mobile phone base stations as illuminators for passive radar. So you have a globally available infrastructure. That means you have globally available radar illuminators. That's a good idea for passive radar. So consider these and receive them, well, with a distributed sensor network, several receivers. And we in Germany, Defense R&D, we are very much interested in harbor protection. That's an area where we are much involved. We're interested in very small and highly agile boats attacking ships, German ships in harbors. Ships in harbors cannot use their active self-defense radars. That would be high-power microwave, something like that. So they need passive reconnaissance, and there are many illuminators in the harbors. You see here the harbor of Eckernförde. Eckernförde, this is the German marine harbor, and we are here, it's well illuminated by GSM base stations, and we are considering one receiver, another receiver, and the combination of 2 receivers to observe a very agile and moving boat here. What you are seeing, oh, it's not moving. Is it not moving? It moved before I tried it. Sorry, it's always the same. This is why I like to use my own computer. So what you should have seen here is a passive radar and a boat moving here, working not so well, and using it with a distributed sensor network. The boat is well tracked, actually. So distributed fusion. And the key to it is algorithms, distributed fusion algorithms. This comes. Now I would like to come to an end. I wanted to bring to your awareness the extreme importance of fusion engines. These fusion engines, on a smaller scale, on a bigger scale, they are the key factors, the key bridge, the link between the vast amount of sensor data, which cannot be exploited by human beings without help, and the decision maker, the human being who only is intelligent and who only can be responsible for what he can do. Thank you very much.